Yes, I'm back now.
Sir, welcome back, sir.
Yeah, thank you. So is that still you are facing much noise from my side, or how it is? So I could see there are messages related to noise.
Yes, yes. Now there is no background noise, sir, but voice is little low. Can you speak little loud?
Actually, this facing some problem with mic, I guess, in Google Meet. I just checked before joining also. The mic 100% while I'm talking, but I'm not sure. Is still voice is my voice is low, or
Still, it
uh,
is little bit low, sir.
okay. Oh, now is that clear now?
Yes, sir. Little bit improved, sir.
Okay. So let me share my screen again. So a quick recap. Okay. So quick recap. What we discussed. So as of now, we discussed about the uh, quantum cryptography and what are existing cryptography mechanisms, and what are the principles of quantum cryptography, and how what is the difference between classic and quantum cryptography differences we discussed. And now here the quantum cryptography alternative approach for post quantum cryptography, which is an algorithm. Post quantum cryptography will uses a quantum mechanics. PQC consists of classical algorithm believed resistant to quantum attacks.
Sir, now voice is clear, sir, but PPT is not in full screen mode.
Okay.
Now it's everything fine, sir. Thank you very much.
Yeah, thank you. So this is NIST is currently standardized PQC algorithm based on lattice-based cryptography, hash-based cryptography, code-based cryptography, and multivariate polynomial cryptography, Ashogni-based cryptography. So there are alternative approaches to do the secure transmission of data from source to destination. These are the NIST is currently standardized PQC algorithms based on these cryptography models. So implementing quantum cryptography for ML systems. So risk one is the first thing we just need to observe is we just need to consider is risk assessment. Identify which ML assets require quantum level protection. Consider model IP, training data sensitivity, and the regular requirements. So in the terms of ML machine learning systems, so the quantum implementation of quantum cryptography, we should consider the following aspects. Risk assessment. First, we need to do the risk assessment, identify which ML assets require quantum level protection. and consider the model IP and the training data sensitivity and regularity requirements. And the second one is we can implement using a hybrid architecture, implement quantum key distribution for key exchange while using post-quantum algorithms for bulk encryption of model for sensitive training data. And integrate with PKI, combine quantum key distribution with existing public key infrastructure to create a transition pathway rather than a complete replacement. And there is we need to one more aspect we just need to consider while implementing the quantum cryptography in machine learning as performance optimization. Use quantum derived key selectivity for critical operations while maintaining classical cryptography for less sensitive, high throughput ML interfaces. So these four aspects we need to consider while implementing the quantum cryptography in ML systems. And the feature of quantum cryptography. So as we discussed, the quantum cryptography will use the transmission of keys from source to destination in form of photon transmission like cable media or open air transmission. So the feature of quantum cryptography, like quantum repeaters, will extend KQD beyond current distance limitations, enabling true quantum network spanning nets. So as we discussed earlier, so this quantum cryptography sharing of public key approximately 100 kilometers, and that is limited to when we use quantum cryptography implementation using fiber optic cables. But that will extend KQD beyond current distance limitations, enabling true quantum network spanning continents. Integrated photonics. So will dramatically reduce size and cost of quantum cryptographic systems, enabling deployment on edge ML devices. And quantum internet will create a global infrastructure for quantum secure communication, enabling new distributed ML with unbreakable security. So we can work towards quantum internet. Will create a global infrastructure for quantum secure communications and with unbreakable security. So physics-based security, implementation readiness, hybrid approach. These are the key takeaways for this quantum cryptography. So physics-based security, quantum or cryptography achieves security through the laws of physics rather than computational difficulty. And implementation readiness. KQD systems are commonly commercially available today, but have practical limitations in distance and key rate. And there is a hybrid approach, combine quantum and post-quantum techniques for comprehensive ML system protections. So these are the key takeaways in this one. And these BB84 and D91 protocols we already discussed. This presentation of explorers the foundation of quantum cryptography through the BB84 and D91 protocols. So these all are like our HTTP, HTTP4 protocols to implement this quantum key distribution QKD. And these methods revolutionary secure communications by leveraging the fundamental properties of quantum mechanics. The quantum advantage in cryptography. So the advantage of quantum. The classical cryptography relies on computational complexity, while quantum cryptography leverages the fundamental properties of quantum mechanics. So these theorems we already discussed, no cloning, and we cannot create an exact copy or identity of particular photon transmission from source to destination. And no cloning theorem prevents copying of unknown quantum states, and measurement distributes quantum systems in detectable ways. For example, from the source side, if zero transmits and destination zero, the destination side, the destination should consider only zeros. So if it is one, then send to the garbage. So, and the quantum entanglement creates a correlation that can't be explained by a local hidden variables. And security derived from physics, not computational assumptions. The BB84 protocol is the first quantum key distribution method developed by Charles Charles Bennett and this is also this already we discussed. The BB84 protocol is used to implement the quantum key distribution. This is one of the method to share the keys from source to destination securely. So BB8 keyboard distribution step by step. This is already we discussed. This uh, the practical implementation of polarization encoding. The common implementation uses photon polarization states, horizontal 0 and vertical 90 degrees for rectilinear basis, diagonal 45 degrees and anti-diagonal 135 degrees for diagonal basis. Single photons carry quantum information between parties. Parties from source to destination, the source to destination are here are the parties. So when you say transmission of horizontal 0 degrees and vertical 90 degrees, this we can call as a rectilinear basis, and when it transmit diagonally 45 degrees and anti-diagonally 135 degrees, for this is we can call it as a diagonal basis transmission. So single photons carry quantum information between parties. The photons will carry the quantum information between source and destination. So BB4 protocol implementation often use specialized hardware, including single photon sources and detectors, and we can say like phase modulators and interferometers, and polarizer controllers and beam splitters. So BB84 protocol implementation often uses all these specialized hardware. So Evers dropper detection in BB84. Evers dropper intercepts even. So Evers dropper cannot, as we discussed, cannot change the state of that particular photon, which is transmitted from source to destination. This is Evers dropper. Why they are not able to intercept means, so when, for example, 0 is coming from the source side and the destination side, we should also expect the 0. It's not 1. So there are measuring techniques which are at destination side, and those will keep on trying to get the value which is shared from the source. For example, if it is 0, that would expect 0. So if the someone EVS dropper is trying to capture the information, that can be elected to source and destination. That cannot be altered. So how that will happen in BB84? This is the EVS dropper intersects. Even Eve intercepts and measures qubit sends from alias to Bob. Error detection. Alias and Bob detects error by completing subset of their key and force-based choice, qubit regeneration, and quantum distribution. So by using all these techniques, we can detect the EVS dropper. So there is one more protocol other than BB84. This is a E91 protocol, quantum cryptography using entanglement. So this E91 protocol offers a profound security advantage. The security is based on fundamental non-locality of quantum mechanics and can be verified through Bell's inequity tests, making it particularly robust against certain advantages of attacks. So this is one more protocol to implement the quantum cryptography using it uses entanglement. Quantum entanglement, the foundation of E91 the protocol. This quantum entanglement is the foundation of E91 protocol. So the correlation persistent regardless of separation distance. This was we can see in the physics, like this cannot be used for faster than light communication. Means this cannot be transmitted as light.